Hey guys, it's Mr. Eidsness here, and we have chemistry coming up. All right, this is my background. I love chemistry. I'm super excited to teach you guys all about the atom, and basically every single part of it. So I hope everyone is doing fantastic, enjoying um, the freedom to kind of be at home. I know things are a little bit different, but we're gonna figure it out. All right, so let's get at it. Let's talk about the atom. I'm gonna bounce back and forth, just so you know. This is what your notes should look like. This is kind of what we're going to cover. Is going to be this page called the atom, and all the way down, including this blank space, will be at the very end. There'll be some problems for you to practice, all the way down to the end where you see this fluorine here. The sum it up page we're not going to cover in this video. So if that's what you're looking for, this is not the video for you. We are going over the atom, its basic parts, and including these couple of pages here. So you're going to kind of fill in the notes as we go. I'm going to do my best to point out what you should be writing down. But obviously you can always pause, rewind if you didn't catch something. So let's get into it. The atom. So what important information does the periodic table tell us about the atom? So number one thing that we need to look at here is we're going to have three parts. Okay, we call them subatomic particles of an atom, and we'll get into them very, very quickly. But we have our positive one, which is going to be the proton. We have another similarly sized part of the atom, which is going to be our neutron. And then we have a almost massless or super, super small and fast moving particle within every single atom. Well, actually, sometimes they lack electrons, but this would be, I wrote a little negative above the E because it is a negative particle, but we call this our electron. So this is just kind of a general overview before we hop into our notes here. Another thing I'd want to point out is if you haven't watched how small an atom is, go ahead and check that out. I'm not going to show that video right now, but it does give you some perspective on how tiny these things and what we're talking about. I know in life science we talked about cells and how small they are. We are talking about like when we did our cellular respiration and photosynthesis, when we're talking about H2O, we're talking about every single symbol is representing an atom that builds up what an H2O molecule represents. So I know I'm talking about all kinds of stuff right now. This is kind of our overview. Here we go, moving forward. All right, first slide. So the smallest part of a chemical element, matter, that can exist, that would be an atom. Okay, so it is the smallest part of matter. Okay, anything you can touch or feel is going to be that takes up space is what we call matter. Okay, anything taking up space is going to be matter. So everything's made up of atoms. All right. Now the word atom comes from a Greek adjective called indivisible. Okay, not invisible, like you can't see it, because you can't see atoms unless we have an electron microscope, and even then it's really hard to see them. But it's indivisible. And so the idea is you can split something in half. Okay, so we have our little block here. You can cut it in half, and then you can cut it in half again, and then you can cut it in half and again, and then you can cut it in half again, and then you can keep cutting it in half, and eventually you won't be able to cut it in half anymore. Okay, it is absolutely the smallest thing you can possibly see. So it is indivisible. And so that's kind of the idea behind the naming of the atom. All right, let's move on to our next slide. So now we're getting into the bulk of our notes here. All right. The concept of an atom has changed over time, okay? As we have gained more knowledge, as we've done more experiments, we have gained more information on what an atom is and how it works, all right? So I would like to point out that we have the names of these theories are listed right here, and then the time that they are founded. And so I believe in your notes you're going to have to cover either the name or the dates on here. Make sure you're able to write those in as we go here. But basically, right away, you can see we have these different theories, and slowly we're getting more information, and we're understanding more about atoms and how they interact with one another. So at first we kind of thought atoms were these tiny little billiard balls, if you will, if you play pool. But then we found more about the particles inside those balls. And so that's why we have the chocolate chip cookie theory, okay? Because now we start thinking about the other particles, because it's not just one ball, okay? We have our protons, we have our electrons, and we have our neutrons, okay? Now we have the cherry with the pit theory, leading into our solar system theory and the Bohr model. The Bohr model is very, very interesting because it helps us understand exactly what we're talking about and what we're looking at. Okay, we're going to go into Bohr models in another video, and experimenting. The Bohr model does a great job of showing us where electrons are and helping us visualize it. Because when we get to the cotton ball model, the one that is accepted at the moment, basically it gets very, very complicated very, very quickly where electrons are within an atom. And so basically, over time, what you need to take away from this page is over time, we get more information and we're able to get a better description or have a better representation of what an atom really is. Okay, so let's keep on moving. So looking into what is within an atom. All right, what is within an atom? So what are the subatomic particles? Okay, we say subatomic because it's the parts. That's what sub means, okay? The parts that are going to make up an atom, okay? Subatom, subatomic. And so what are those particles? Okay, we mentioned them very briefly at the beginning of the video, but let's just go over them once again. So we have our proton and we have our neutron, okay? It is not a mistake that they're drawn the same exact size, okay? We'll get to that in a second when we talk about mass. You can see their mass is literally the same at 1 AMU. But the thing that you need to know is think of positive, okay? A pro to making a decision versus a con is a positive thing, a good thing that's happening. Whereas neutral, okay, you put your car in neutral, neutron, okay? So you just read that very beginning of the word and it kind of tells you what is the charge, okay? You can have a positive charge, you can have no charge, which is why neutral is represented by a 0, okay? Represented by a 0, or you can have a negative charge, which would be the opposite of positive. And so you'll see these charges become very, very important as we talk about interactions between atoms. We're not going to do that in this video at all either, but basically the charges between the proton and the electron, which is going to be our negative subatomic particle, they cancel each other out. And so we'll teach you by the end of this how to count the positive charges and the negative charges and then kind of figure out what's going on. Also, when you see symbols, okay, proton is always going to be used by a P, neutron is always going to be used by an N, and electrons are always going to be used by an E. All right. Let me just erase some things. I think it's getting a little crowded here. But it will always be followed up with its charge in the upper corner, kind of where an exponent would go. Like in math, you see like x squared, okay? Or you see like x to the third or something like that. We're going to, with our symbols, we're going to kind of show always P is going to equal protons, and I always write the charge up above it, okay? Usually when I do the neutron, I do put a little arrow through it to remind me that it's null and void, okay? There's no charge to it. And then electrons, I like to depict them as a lowercase e because I know they are smaller, and that helps me remember that, as well as the negative sign for representing the charge of an electron. Now let's get to mass. Mass is super important, okay? Because we are talking about very, very small things, right? Something that's a part of an atom, okay? Very, very small things. So scientists recognized right away that it was going to be very difficult to talk about the mass of these different atoms, because they are different, unless they make up a convention, something that they can agree upon to talk about it a lot easier. Or else, every single time they see a proton, as you can see here in my Google search bar, okay, they would have to write down this number, okay? -27. So that means you would put a decimal point, okay, and then you would have as many zeros as it takes to represent negative 27. So you'd have point, so it'd be 0 point, and then you'd have 27 zeros continued. Okay, you can see where this can be very, very difficult to add and subtract these numbers and do them very quickly. So luckily, protons and neutrons are very, very close in size, like extremely close in size, and so we're able to just call it an atomic mass unit. Okay, and so basically we're just saying because basically the only thing that we're adding is going to be our protons and our neutrons, we're able to just kind of round to the middle and just say, all right, protons and neutrons, they are both equal to 1 AMU, and electrons effectively are 0, do not have any mass compared to the protons and the neutrons. Electrons do have mass, or else they wouldn't exist. But when we do our calculations, when you guys are actually doing problems and you're taking your quizzes and tests and whatever, and we ask for the atomic mass, okay, the only ones that give you atomic mass is going to be your protons plus your neutrons. Okay, those are the only ones that are going to give you mass. So let's keep on going. But those are going to be your subatomic particles that we're going to be referring to, and you are going to need to understand and memorize what's going on here. All right, so moving on. Okay, where are the subatomic particles? Okay, where are the subatomic particles? Where can we find them? All right, well, there's going to be two parts of our atom. All right, there's going to be two parts. There's going to be our nucleus, and then there's going to be our electron cloud. All right, the nucleus is just like in a cell, is going to be the very center. It's going to be the very middle of our atom, and this is where you're going to find the protons. And you're also going to find, and remember, protons are going to be positive, and you're going to find your neutrons. Okay, neutrons, remember, are going to be no charge. All right, they are both going to be found in the center. So you can see in this picture, let's see, I will choose red to be my protons. Okay, I'll just draw in my little key here. The red is going to be depicted by the plus signs. So what you should do in your notes is you should color in all your protons. They are found in the nucleus. Okay, they're the positively charged particle, and they're pretty big. All right, they're pretty darn big. They are 1 AMU. Okay, 1 AMU. Both of these, remember, protons and neutrons. Now, the ones that are left blank that are going to be in the center of our atom, all right, those are going to be our neutrons. Okay, those are going to be our neutrons. So let's just color that something else. Let's go with the blue. Okay, neutrons, we're going to make that blue. Okay, but these are going to be particles that do not have a charge, okay, but they do take up space, and they do give mass, or I shouldn't say weight, but they do give mass to the atom. All right, and they're going to be very, very important as we move through and talk more about the periodic table and how it impacts different elements. All right, lastly, there are the electrons, and now the electrons are, as it shows, are located in the electron cloud. Okay, so the electron cloud. And that is just going to be something that is around the nucleus. Okay, they are massless, okay, meaning 0 mass. They have 0 AMUs. Okay, they are super tiny. Now they're also super, super fast. Okay, you will see them for our experience in these little rings. So I'm going to draw them as an E with a negative next to it to remind myself that is a negative charge. Okay, that is a negative charge, and they're gonna circle around the nucleus, especially in our Bohr model. That's what you are seeing right here. This is actually a Bohr model, and we will talk more about Bohr models in another video. But this is kind of our general depiction of what an atom is going to look like. Okay, it just makes it easier for us to kind of figure out, okay, all the mass is within the nucleus, which is in the center of the cell, or not the cell, excuse me, the atom. whereas those electrons, they're flying around the outside of that nucleus, and the electrons wind up doing all the interacting with other atoms. Okay, when we finally talk about reactivity and how atoms are actually, because everything you do in the world, you're having atoms interact with one another. Every time you pick something up, anytime you mix something. Now, granted, sometimes you're going to have a chemical reaction, and sometimes it's only going to be a physical one. And we'll talk more about that later as well. But keep that in mind. Anytime you touch something or interact with something, atoms are going to be interacting in some way. So when you look through this paragraph up top, make sure that you get down the Bohr model. Okay, the Bohr model. And then I believe dense is one of the words as well. So that nucleus has all the mass, meaning it is very, very dense compared to the electron cloud. The electron cloud is almost all made up of empty space. Okay, and so actually, because if you watched the video here from slide 1, you'll know that the size of the atom, most of the atom is made up of empty space. So let's keep on going here. Now that we know all about our subatomic particles and where to find them, now we have a system that's going to help us understand the data that we need at all times. We call it the periodic table, about all these different elements, and it'll help us solve problems. Okay, it'll help us understand what's happening, especially when we start dealing with chemical reactions here in a bit. All right, so reading the periodic table. Yes, we're talking about this periodic table right here. All right, we got all kinds of elements. Typically, you'll see it depicted in different colors. But what we want to look at and examine is, all right, if we choose one element and we zoom in all the way, okay, we're talking about just one of these boxes. Okay, so element 26 is going to be iron. Okay, so we're going to be talking about, all right, what does this mean? What does 26 mean? What does Fe mean? What does the name mean? And what is this number down here with this decimal place? Okay, that's what we're about to dive in and understand. All right, so let's go in here and figure it out. So first, the letter is just going to be the chemical symbol. It helps us so we don't have to write out fluorine every single time. So instead of writing out this entire word of fluorine, we can just make a symbol that is going to say, hey, we're dealing with fluorine, and we just use the word or the letter F. Okay, now in the top corner, okay, this is going to be the indicator of what element fluorine is. So fluorine is element number 9. Okay, its atomic number is number 9. Think of that as your ID. Okay, the ID says exactly who you are. The atomic number says exactly who you are. Now, keep in mind, where do we get that number from? Why just choose 9? It's not random, people. Okay, we're actually looking at the protons. So remember, the protons, they are a positive particle, and they are going to be the, you'll see in a future slide, they're the fingerprint. They are unique to every single atom, okay, and every element. So if you are an atom of fluorine, you have to have 9 protons, okay, or else you're not an atom of fluorine. All right, so if you see an F, the F is telling you, hey, we are dealing with fluorine. That means we have 9 protons in the nucleus of the atom. Okay, so 9 protons in the nucleus. We're dealing with the element fluorine. And then this bottom part is actually going to be our atomic mass. Okay, I'll give you a second. Maybe you want to pause the video. What 2 subatomic particles make up our mass? All right, gave you a little second there. If you said electrons, you're wrong. It's not electrons. Remember, electrons are going to give us 0 AMU. All right, so it's actually going to be our other 2. So it's going to be our protons. Then we're going to add our, actually, I'll write it in another spot. I don't want to confuse you guys. But atomic mass is going to be equal to protons, which are positive, with our neutrons, which are going to be our neutral subatomic particle. And so that's going to give us our atomic mass. And so using this formula of atomic mass is equal to protons plus neutron, or not proteins, protons plus neutrons, we're going to be able to solve for any one. So as long as I give you the amount of protons or tell you the element or give you the amount of neutrons, you should be able to figure out the mass. All right, and so that's kind of what our practice problems are going to get down to. All right, so let's keep on going. All right, so topic question number 5. What does the periodic table tell us? So the periodic table is super handy because it's going to tell us a number of things that we looked at in the last slide. All right, it's going to tell us our atomic number, okay, which is the number of protons. All right, and when we're trying to figure out the number of electrons, I know that's not listed on this page, but you are going to need to be able to find the number of electrons. Okay, remember protons are going to be positive, okay, and we need to cancel those out. So we need a neutral fluorine atom, and so what happens is we're going to need 9 electrons. All right, because electrons are negatively charged, and negatively charged particles are going to cancel out the protons. So then we have 9 of each here. All right. And now we need to figure out the amount of neutrons. And so that's where our atomic mass is really, really nice and is useful because we can use the atomic mass, okay, to find the mass number. All right. The mass number is important because now we'll be able to use whole numbers, and we'll be able to use a little bit of math to figure out what our mass is, okay? What our amount of neutrons do we have in this atom. So with our mass number, what we're going to do is we're going to round. All right. So for the most part, most of the atoms are going to be really, really, like it's going to be 0.998, and that's going to be pretty common to see. Or you're going to see 0.1 or 0.001, something like that. All right. So those are easy. We round 18.99, we round that to 19. All right. One like let's see, like 16.001, that's pretty easy. We're going to round that to 16. All right. What about if we saw one that was 15.5? What are we going to round that to? Well, if it's 5 or up, we are going to round that to, if the 10th place is 5 or higher, we're going to round up. So 15.5, we're going to round that up to 16. Okay. But let's say it's 15.45. Well, that's a tough one then. And what I want you guys to do is we are going to round that down to 15. Okay, so you're just looking at the 10th place. Is it 5 or higher? All right, we're going up. If it's 4 or lower, we're going to stay down. Whatever number we have, we're going to stick with. All right, so keep that in mind moving forward because this isn't the only example that you're going to see. But when we're looking for the mass number, it has to be a whole number. Okay, it has to be a whole number. Okay. That is going to allow us to run our equation to find how many neutrons there are. So I'm just going to kind of allude to it quickly on this slide, and then the next slide we're going to go a little more in depth on how we're going to find this number. But basically all we're going to do is we're going to round. In this case, we go from 18.99, we're going to round to 19. Okay, we're talking about fluorine here. And then we're going to subtract the number of protons. Okay, 19 minus 9, and that's going to give us 10. All right, fluorine must have 10 neutrons. Now, you'll notice, all right, neutrons and protons, okay, are the only ones, okay, neutrons plus protons are the only ones that give us mass. All right, they're the only subatomic particles that give us mass. They are both equal to 1 AMU. Why aren't we including any of the electrons, guys? Well, the electrons don't have any mass. They're equal to 0 AMU, so we can't include them in our mass number. All right, so let's go on to the next page and just start to dive into a few problems, and I think it'll start to make a lot more sense. Okay, so let's get rid of everything that I've written previously. All right, so looking at this example right here. All right, we're talking about carbon. So number one thing I need to point out, it doesn't say carbon here, does it? It says lithium, right? So that's a different element, but we want to do carbon. So I'm going to write carbon on the side because that's going to show our picture right here. So we use a technique and something to just help you remember, okay? So we use ape man. And so what you can do is you can just write this out, and it will help you figure out exactly what's going on in how we can find the atomic number, the protons, the electrons, and then the mass atomic number and the neutrons. So the first thing we're going to do when we see carbon is we're going to write out our ape. We're going to write out our man. And now we're going to find solutions to these. So ape, that is the A in ape, is going to represent our atomic number. All right, our atomic number. So what's our atomic number here? It is the 6. Okay, it is the 6. We have 6 as our atomic number, which means we must have 6 protons. Okay, 6 protons. Now, as we get down to it, we also are going to have 6 electrons, because we talked about protons are positively charged, electrons are going to be negatively charged, and we need to cancel them out. Okay, we need to cancel these two out, and so we need to have the same number, because if we had more protons, we'd be more positively charged. If we had more electrons, we'd be more negatively charged. Okay, so keep that in mind. We are always going to deal with neutral atoms in this class. Okay, we're always going to deal with neutral atoms. Now, let's go to our mass part. Okay, so our man. So we did ape, done deal, 666. But now let's talk about mass, or man. So we are talking about the mass number. Where do we find our mass number? Well, we find it right here. And now this is already in a whole number for us, so it makes it a lot easier. We don't have to do the rounding part like we did in the last slide. Okay, so it's just 12. All right, now we're going to figure out what is the atomic number. All right, well, we already pointed it out earlier. It's got to be in the top corner, and that's the amount of protons that we have. Okay, we also listed it right here. All right, they're always the same. Atomic number and amount of protons are always the same. So it could be atomic number, it could be protons, but we just, ape man works a lot easier to remember. So that means we got to put a 6 here. And now what you're going to do is a little bit of math. All right, you are going to subtract 12 minus 6 to get the amount of neutrons. Okay, so you're going to wind up with 6 neutrons. Now, when the mass number is different than 12, okay, like let's say this was 13, okay, this 12 was actually 13, okay, we would still have a 6 here. All right, I think a lot of people go wrong because they just see that, oh, for carbon, we have 6, 6, 6, 6. No. We still got these numbers by doing specific things. So let's keep on moving. I'm just going to erase a few parts, and let's move on and talk about lithium. So I want you to find your periodic table, and I want you to try lithium by yourself. Okay, so if you go to your periodic table, unfortunately, this periodic table has some writing on it. Oh, I got some more on it. But lithium is going to be in the top left. It is actually the third element. Okay, it's depicted by 6.94 as the mass number, and then the atomic number is 3. All right, so I do want you to go ahead and try lithium by yourself, and then we'll show you the answer here in a second. So I'll wait 2 seconds, and then we'll go to the next slide. All right, so hopefully you tried it out, but this is how we are understanding what lithium is. It's kind of broken down for us really, really nicely here, but we're finding our atomic number, 3. Perfect. Atomic number is always equal to the amount of protons. Perfect. We always need the same amount of protons, positive, as we need negative. Okay, so they can cancel out and give us 0. So 333. Awesome. Now we got the atomic mass. All right, also super important. Because we're going to take lithium, which is 6.94, like we showed you right here. Okay, 6.94. And we're going to round that up to 7. Okay, if you don't round that up to 7, you're wrong. All right, now we're going to subtract our atomic number, which we already found out to be 3. Okay, and now we're going to get the amount of neutrons. All right, so a lot of different problems are going to ask you all these different questions. So let's go ahead and let's try nitrogen, let's try francium, let's try lead, let's try potassium. The elemental symbol is going to be N, capital F. Sorry, I drew that really, really horribly. Okay, it'll be capital F R for francium, and it'll be PB for lead, and it'll be a K for potassium. Okay, that's just the way the Greek words kind of work out. They're not always, it's not P, K, it's a K, but it's just a little bit different. So take some time, work through all these problems, do your 8 man for all of these, and then we will find the answers here in a second. All right, so 3, 2, 1. All right, so make sure that you're doing your 8-man. You're able to figure out the amount of protons, electrons, and neutrons. Now, a few things that I want to point out about these answers before we wrap up. Okay, protons, again, I'm going to keep stressing it. Positive. Electrons are going to be negative. They always cancel out. They always have the same number. Okay, our positive and our negative always are going to be the same number throughout this entire thing. You can see this. Okay, positive, negative. Boom. Now, the protons and the neutrons are the same here, okay? 7 and 7 on nitrogen and 87 and 87 on francium, but they're not always the same. Okay, that's a huge misconception. All right, here we have 82 and we have 125. It's a big difference. Okay, or here we have 19 and we have 20. With this information, we can also find the mass number. Okay, so if we're looking for the mass number, okay, we would just have to add our protons and our neutrons. Okay, so we'd get 14 again, or 87 plus 87 is going to be 174. Okay, 82 plus 125 is going to be, let's see, 207. All right, 19 plus 20 is going to be 39. These are going to be the mass number. We can just calculate that very quickly, because do the electrons count in the mass number? No, they don't. Okay, electrons do not count in the mass number. So I know there's a ton of information here. If you have any questions, make sure that you get them answered, and make sure to ask questions if you have it. But good luck moving forward with your homework, and I'll see you guys in the next video. Bye.